So today we'll be going through an intuitive way of EKF, which is used in localization, which is used in sensor fusion, which is used in multiple filters in sensors. So we are not going through the derivation, but we're looking towards an intuitive way of how EKF works. So apart from the localization and state estimate, EKF is basically an problem of formulating where the states are. So this is an estimation problem, and apart from them, it also goes with the prediction as well as interpolation, filtering, and smoothing. So let's start with an example. So let's say we have a robot which has a differential drive. So here we consider as a unicycle model as we are doing a simulation. So we consider it has moved with some input u, and we are considering it as a Gaussian, as a probability and Gaussian estimate. So here we are talking about how we will get it as a predicted state estimate, and how will we get the measurement of the model, and how we will be predicting that what is the proper estimate of the robot when we give some amount of input u. So hereby we consider it as like u as input, and we approximate that we get some state estimate from, let's say, GPS. So throughout we will be considering a GPS, but we can get from any of odometer, IMU. We can use them considering like what sensors we are having on the robot. So, but what we can say, like, for example, in GPS might not have that much of frequency. It might have a low frequency, or it might have a like lot of noise if we consider another like gyroscope. So what we will do? So we will be having another estimating model. So here we consider as a mathematical model or a motion model, where we have x hat, which is the estimated state, and what we do, we consider a Kalman gain. So here we are introducing a Kalman gain K, which is basically what we're doing here is converging what we get as a x hat, a predicted state estimate, and what we get from our observation, which is like a GPS or any kind of a sensor. So here are the equations of the predicted states and as well as our observation. So here we consider WK and VK as a noise, which is basically a measurement noise and a process noise, a Gaussian estimate with a standard deviation of Q and R. So Q and R are the measurement model and the process model, which are tweaked according to what our noise of sensor is. According, it would be different for IMU, it would be different for GPS. At whatever sensors we are using, we have to go through a ground level research of what noise it has. So we'll be tweaking those Q and R according to that. So this is some of the implementation stuff what we will be doing further. That so we are considering an emotion model, and we are considering it as a non-linear unicycle model. So because of its property of non-linearity, it would be going like F would be identity matrix, as we don't have any linearization, and B is equal to cos theta sin theta dt, with our state as a x and y as a position, theta as a yaw, and v as a velocity, and we will be giving our u as velocity and omega. So finally, we will be seeing our unicycle model as v cos theta, v sin theta into the timestamps what we are going through, and omega. So here we consider a difference between a Kalman gain and what we say as a Kalman filter and a EKF, which is extended Kalman filter. So what we do here is to linearize the non-linear, or we can say a local linearization of a non-linear model. We do a Jacobian of the motion model and the measurement model. So the motion model, so the Jacobian is basically what we do. We do a partial differentiation of function with all the variables we have in the function. So here we can see x, y, theta, and v are like partially differentiated with each other in Jacobian. And we also consider a measurement model. So here in measurement model, measurement model, what we consider is there is no transformation currently being taking place. We are considering directly what we are coming in from the GPS or IM. There is no transformation here. So if there is no transformation, we are considering it as identity matrix. To get a more intuitive way of how this thing will work, so we consider it as a second order Markov-Nikodym chain. So we consider it as a second order as we have a q as an input and a measurement that is a z, which is dependent on x. Like they both are dependent on x to find out the state. So if we see the equation here, it is a basic Bayesian equation where we say that if we want the probability of the state, we have to with the given measurement as well as what we have given as an input u, we will be requiring the likelihood, the prior as well as the normalizing constant. So yeah, to find out these things, we required we required basically a equation where we can find out this thing. So we were not getting into more detail about how we'll be getting this thing, but through Chapman Kolmogorov equation we can get this. So yeah, we can see that the corresponding equation is how we find in the Kalman further in the Kalman process. So here we say we don't use the direct equations. We say it as a Gaussian process. We approximate as a Gaussian process and not directly use them, as it would be much more calculative intensive. So here we can see this is the main formulation of EKF, we can say, and we will not go into the much more detailed process how it is derived, but we can give an intuitive way. So the predicting state, we estimate the state through our unicycle model, which is the motion model, as well as we predict the covariance. So in the covariance, we use our Jacobian matrix, which is the FK, as well as the process model noise, which is the QK. So after getting the prediction from our motion model, we go with the measurements. So here we are having a error that is the residue of the measurement, which is YK. So here we are subtracting our measurement with our motion model. So they both will be giving some state which might be overlapping as well as it might not overlap with each other. So this is what we get an error if they are overlapping or not. So here we find SK, which is basically used in the formulation of the Kalman gain. So again, we're not getting into the details of the how it is derived and why is it like that, but we are getting an intuition of what every step is meant for. So here we use for SK we are using the covariance with the HK, which is the Jacobian of the measurement model, as well as the measurement noise, which is RK, and we will be getting a Kalman gain matrix with like the covariance into the measurement transpose and the inverse of the S. So this is the Kalman gain which will be used for the correction now. So we have predicted whatever we have we are updating it. And so now in updating the state estimate and the covariance estimate, we are basically plotting our new error into the Kalman gain what we have, and we'll be finding out the updating or corrected estimate through like the inputs as a predicted state as well as the measurement model. So in the last two steps, we are basically updating our state and finding out its covariance. So here we can see that from the previous, like it was here, and you can see in the previous, we find out from the Bayesian method that we want the state and the covariance, and as well as the next state and the covariance. So to get the formally what we are doing and to form our the intuition of EKF, we will further going through the code. So we'll further proceed with the code of EKF, and these are some of the variance covariances metrics which we'll be using further in the formulations. And here we are taking u as input vector, and we'll be considering velocity as well as omega, that is yaw rate. We are considering a circle of radius 10 meters, which will cause u as omega as 0.1. Then we will be further going to the motion model, which we'll be using as a unicycle model kinematics for simplicity of the example. Then we will be using observation model as well as the Jacobians of observation model as well as measurement model. So these are the part of the formulation which we just skipping through it. And we have observation as a GPS, so we'll be adding some random noise for the sake of representing a GPS, as well as some white noise with the zero mean, which we consider inside the formulation here. So there are the major steps like a predict and update. So predict will predict where the state is, and update will update with the observation model what we are considering. So here we go.
Yeah, they didn't want to. I think they running where's the code.
So here what we are doing is we are simulating through particular time frame as a dt. We consider as a steps. So we'll be taking consideration GPS as well as the kinematics, and we will be making a EKF filter with these two measurements. For the sake of simplicity, we are taking just two measurements right now. So here we can see the results. So we can see that here we can see that the GPS measurement, which is about which is very noisy, as well as far as it is just dense, but sometimes GPS are not that dense. It can be like very, very sparse as compared to what we can see here. But as we can see that the kinematics which we are getting is blue line, and which is like a bit off, but we can see the comparison between the kinematics and GPS, which is not that much. But to stabilize both of them, we use EKF filter here, and we can see that a smoothness which is given by the EKF filter throughout